This week I worked on problems for chapter 3 of Thomson, Bruckner. Did a sample of the problems. Didn't do as much of a coverage as I did for chapter 2 because I'm realizing that I need to cover a lot of chapters and I have limitations with time. So I have to, this is the reason why when you take a class, the professor does not assign every single problem in the book. Now I'm learning the hard way, of course. That's the issue. So then to the book and the problems. It's been sequence problems and infinite sums all the way to, of course, using the Cauchy criterion. Of course, it's all about summing over the tail. Well, first it's just for an infinite sequence, and then the Cauchy criterion for an order sum, in which case you do get to sum the tail between n and m. And I was just looking at it. There it is. Yeah, there it is. Right there. So the basics of when you add two sequences that are themselves divergent, you can get a convergent sequence of various different combinations. And I've started on the test for convergence, and that's going to be a lot more work. And also in the section for test for convergence, I plan to do more problems per section for the section. And I'll show speedback for one problem. Then here is, and this group of problems, I'm up in this group of problems. I'm up to 28 pages for the problem set. I like long problem sets. Some of the pages have some what I would call scratch work, but I keep it in because I like to see my process of how I do something. Let me put speed back out because it's only going to come in for one problem. So starting in chapter 3, working through sequences. Okay, here's where feedback comes in. So the whole business of how do you calculate these higher orders of the sum of k to a power. So k is n times n plus 1 over 2. K squared is 2n times n plus 1 times 2n plus 1 divided by 3. And then k cubed is n times n plus 1 divided by 2 all squared. So how do you get that? And so in speedback, this is discussed in a great problem, and I did figure it out. Took me a little bit to figure out what it was, and so you sum the differences between the n plus 1 term and the n term all the way through, and then when you add them all together, you get telescoping. So you get the last term, n plus 1 to the cube, minus just 1, which is the very first term, and it equals this equation using this algebra. And this is your unknown. Took me a little while to know. Your unknown is this 1 squared plus plus n squared. So this is how you figure out the n squared formula. And then you do it again, and then you put into the fourth power, and you work out the formula for the fourth power. And then the unknown is this right here. And that's how you derive it. So I learned something very interesting. Of course, if I have more time, I would love to do the rest of the problem, but I really need to move on. I need to make good time. I'm beginning to get to the point in this project where I cannot let it turn into a grind. Then the Abel summation formula, there was a problem for it. And yes, I did find yet another instance where ChatGPT got it wrong. ChatGPT gave me an example, and ChatGPT gives like 700 or something for this example. And sure enough, it's really the whole business of subtracting the intersection from the union. So the union of A and B is equal to A plus B minus the intersection. So when you do integration by parts, or when you do summation by parts, the UV in integration by parts is really A plus B. And the integral of V du is really the intersection, and that's why it's negative. And so the same in the summation for the summation by parts instead of integration by parts. And so yes, I worked out an example. Like, okay, I see what we're doing here, and that was very interesting and cool. Then just more sequence formulas. Oh, another instance where I really enjoyed doing a problem, of course, problems are so much more enjoyable than reading, they just happen to take a lot more time, was how to find the closed form for the sum of 1 over k times k plus 2 times k plus 4. Of course, this is from calculus. You break it out into a, b, c, and you find what a, b, and c to separate them. And that's pretty good. I got it wrong the first time. Then I got it right, but I kept getting a factor off. Got all confused, but then eventually I was like, okay, I'm going to just do it again, keep doing it until I got it right. And sure enough, that is the correct answer. 1 over 8k minus 1 over 4k plus 2, 1 over 8k plus 4. But then I started thinking, okay, I gotta get telescoping to get to a closed form. That's the only way to get these to solve. And at first I thought, well, I'll just combine 2 of them and then the other one will be fine. But no, that is actually wrong. The correct trick is to take the 1/4 negative term and break it in a half and do 1/8 and subtract it from 1/8 over k and 1/8 and subtract it to 1 over k plus 4. When you do that, everything folds out real neat, real neat. And so you break it out into these 2 subtractions, and these both telescope. They telescope in a really funny way because the first 4 terms, 1, 1/2, 1/3, 1/4, remain, and you start getting telescoping. There's an offset to the telescoping, and then you get 25 over 36 minus the final term. Boom. That was great. That felt really good because it took me a while to get this. Yeah, it really did. Felt really good about that. Just more, what are the theorems that apply to the various sequences? A couple of problems that I just didn't get right. I just didn't. This is basically scratch paper. I don't know. I'll to be revisited. Definitely to be revisited. Some of these latter problems in the middle of the chapter. A very interesting problem about how if you take, say, a digit out of the harmonic series, you actually do get convergence. And sure enough, you say you take out the 3's, you start seeing how out of a range, like say from 1 to 100, you're taking all the 30's because you're manually taking anything with a 3. But you're also taking the other 9, 3, 13, 23, 43, 53, 63, 73, 83, and 93. You keep doing that, and you're roughly taking away 20% of the terms in the series, and yes, it does converge. Very interesting problem. There's a hint in the back, of course. I didn't figure this out by myself. I used the hint. Then some more proofs where I started, and I kind of felt like, nah, this is not right because it is not two-way. You can't start with the terms are small, and therefore you converge because the terms are small in the harmonic series and they don't converge. So you really always have to go from, you have to assume convergence to show that the terms are small. So you have to do other things to show with the Cauchy criterion that r to the n for r absolute value less than 1 converges. I couldn't figure out the one for the harmonic series. Weak point, even back from number theory. I need to fill this hole someday. Then just started working on some tests using the integral test. I hope it's correct. I think it is. And then there was one problem that required the integral test that looked very difficult to do. But then I said, wait a minute, it's actually a combination of 2 of the integrals that I've done before. How about I mix the criteria for one variable and another? I'm going to go with that. And so here I am on page 28 of the problem set for chapter 3 in Thomson, Bruckner.